Hey, I'm Richard, and we're going to talk about BigO notation. You probably have already encountered this concept in classes like CS 182 or CS 251, but I'm just going to go over a little bit of review and how it can be applied to some topics in competitive programming. So, what is exactly BigO notation? Well, we can classify algorithm runtime into different complexity classes. BigO notation gives us an approximation for how long an algorithm will take to run, and we usually can do this for memory usage as well. For example, if you made like a long array for every single element in an input, then yes, you can use it for BigO notation for memory, but in terms of competitive programming, that's usually negligible because we're usually given more than enough memory. And the way we express it is O of some function of n, where n is the input size. So a few examples of common algorithm complexities. So for example, here we have a linear type algorithm, just a single loop, right, from 0 to n. Or we might have a quadratic time algorithm, O of n squared, from 0 to n and then from 0 to I, right? You might see this maybe in selection sort. And you might say a logarithmic time algorithm where you multiply I by 2 every single time. Or maybe this might be for like something like binary search, like search on a sorted list. And you might also see stuff like O of n log n, or linear arithmetic time. And that would be something for the more popular sorts, such as like quicksort or merge sort. Those are usually n log n algorithms. So in terms of competitive programming, knowing what the complexity of your algorithm is really important for like sort of knowing how to tackle the problem, right? Because when we look at a problem, we're usually given constraints for the variables, right? So let's just say that we have a variable a can be between 1 and 100. And since we are guaranteed that a will be between 1 and 100, we can sort of choose the right algorithm to solve this problem. Remember, in competitive programming, we usually don't really care about finding the most efficient solution, but more like a solution that works, right? If we see that n is just 100, we don't really have to spend a lot of time thinking of an O of n log n algorithm when we could just do a brute force, maybe O of n to the 4th algorithm. If we see a really small number like n equals 5, we could just straight up brute forces like search through all possible combinations or whatever. And if we have a really large n, then we only can like use an efficient algorithm, and that's when you have to spend more time trying to trim down the algorithm into something more efficient. And as a rule of thumb, 1 second is approximately 10 to the 8th operations. So if you can identify the runtime of your algorithm and you just plug like the maximum numbers in, as long as it stays below like or stays around 10 to the 8th, like 1 times 10 to the 8th or 2 times 10 to the 8th, then your algorithm should pass. But if it's like greater, like you have n is equal to 1,000, but you have like an n cubed algorithm, well, that probably isn't going to pass because then that would take 10 seconds, which is usually way larger than the allowed time limit. So how you tackle a problem can actually depend on how large the constraints are. And just remember that we don't really need the most efficient solution, but just a correct one.